Bir saniye, ben bunu değiştirebilirim. View option. Okay, so we will begin. So in the quantum computing seminar, the last part of it was focused on BilQC and sort of the relationship to contextuality and cohomology. This time we will be focusing on classical simulation. And I will sort of, the basic idea behind classical simulation is just that you have a quantum system. Basically, we're thinking of quantum circuit, quantum states, quantum gates, and quantum measurements. And we want to sort of estimate how well we can simulate the outputs of these circuits, i.e. the statistics of these circuits, just using classical computers. And so to this end, there's a sort of a basic sort of, somebody is saying something? Sorry, okay. To this end, there's a sort of like very canonical result, which I will get to by the end of the discussion today. The point is to get to the Gottesman-Knill theorem, which tells you that there's a certain class of quantum circuits which you can simulate very efficiently. I'll just say efficiently, not very efficiently, on a classical computer. So let's just recall, just to give us a little warm-up, that when we have quantum mechanics, we have basically three ingredients. We have the states, we have the transformations. We can think of these as gates, or they're unitary operators. And then we have the measurements. And in general, we think that it should be hard to simulate an arbitrary quantum process or an arbitrary quantum circuit on a classical computer. However, there is something called a stabilizer. So what is called this stabilizer theory, which is sort of a sub part of quantum theory. In the sense that there's a set of states, gates, and measurements. So these are stabilizer states, Clifford unitaries, and I'll explain what some of this stuff is as we go. But basically, there's a subset and Pauli measurements, measurement of Pauli observables. These are sort of a subset of the possible operations, states, and measurements that you can do in quantum theory. And the stabilizer theory is nice in two regards. One is for quantum error correction, which I will not focus on so much here. And then the second thing is going to be what we will focus on here, which is classical simulation. Essentially, we have this theorem. So let me just, this is sort of what we will be focusing on here. There will be a theorem that is the Gottesman-Knill theorem that I mentioned before, which just tells you that if I have a quantum circuit consisting of these basic constituents, the stabilizer states, Clifford unitaries, and Pauli measurements, which I will define all of them as we go, then you can efficiently simulate this on a classical computer. Okay, so I sort of hinted at it, but like so when you talk about classical simulation, there's a basic sort of question that somebody will be wanting to ask is how well can we reproduce the outputs / statistics given through the Born rule of quantum circuits using classical computers. So I do think that it does require saying exactly. I'm not going to be too precise, actually. What do I mean by classical computers? Basically, if you can run a sort of classical algorithm, basically you can think of one of the classical computing models, Turing machines, something like this, like sampling from a probability distribution. So if I can sort of reproduce these outputs of quantum circuits using just these sort of classical methods, how well can I do that, essentially, is the question. And so the idea is that by finding more and more sorts of circuits that you can actually classically simulate, you're better able to understand the dividing line between what allows for universal quantum computation, which we believe to be more powerful than classical computation, by further just pushing out the boundaries of what we know that we can do classically. Just helps us to understand the line between the classical and quantum boundary. Okay, so more or less, the goal when you're looking at something like this is to map quantum states and observables to some sort of classical states, if you will, classical states or operations. By classical, I could mean, and what we'll talk about today is something like a bit string. If I can sort of reduce the action of these quantum observables, namely these Pauli observables that I'll introduce, if I can map these into sort of classical states like bit strings, then I've sort of accomplished one part of this, for example. Okay, so let's more or less get started here. Okay, yes. So let's first define for a single qubit the single qubit Pauli group, which is going to be consisting of plus or minus the identity, or sorry, the imaginary value I plus or minus 1 times these operators I, X, Y, Z, where we have I is the identity. I'm not going to reproduce this one. X is 0, 1, 1, 0. Z is equal to 1, 0, 0, negative 1. And Y is equal to I, Z, X. So what do I mean by this notation, by the way? I just mean that it's the Pauli group consists of these operators, each of which can have the following coefficients, plus or minus I, plus or minus 1. So it's these 4 times all, I guess, 4 of these possible coefficients. And so we have some basic properties about these operators that are useful. So I'll let just sometimes it might be useful. Okay, I'll do it like this. If I have some element of X, Y, or Z, then what I know is that sigma squared is equal to the identity. Actually, I could have done for any element of the Pauli group. Sorry, I can just do it like that. If I have it as an element of the Pauli group, then sigma squared is equal to the identity. I should use the same symbol like this. Okay. And then we also have these, so if I have sigma I, sigma j, I not equal to j, element of x, y, or z. Maybe this is why I used that notation before. We also have this multiplication table, sigma I, sigma j, equals to I, epsilon I, j, k, sigma k. What is this? This is the totally anti-symmetric symbol, basically just saying if I, j, and k are in the same order, or in the lexicographic order, like 1, 2, 3, 2, 3, 1, 3, 1, 2, or maybe that one's, yeah, 3, 1, 2. Then you have a positive symbol here, and if it's in any one of the other orders, then it will be negative. And here, so probably I should have just been more clean from the beginning. This one is sigma 1, this one is sigma 2, this one is sigma 3. Okay, that's another property of the Pauli operators. A third one is going to be that they either commute or anti-commute. So you have that either sigma I, sigma j equals to 0, or you have sigma I, sigma j equals sigma I, sigma j plus. This is the anti-commutator. And we say that sigma j, sigma I equals to 0. So either they commute, so the left-hand side should be more or less familiar. The right-hand side you may or may not have seen. This is the anti-commutator. And so the Pauli matrices either commute or they anti-commute. So we can do something similar. This was just for a single qubit. We can define things also for many qubits. So let's take a Hilbert space, which is the Hilbert space for a single qubit, and tensor it n times for n qubits. Then how does the Pauli group look? It is some subgroup of the unitary group on this Hilbert space, such that it's basically a tensor product of the single qubit Pauli operators. Okay, what does that mean? So as an example, you would have something like if G is in the n-qubit Pauli group, then you have something like the following. Then you have that G equals some overall, this will be some phase, plus or minus I, plus or minus 1. And then you will have the acting on the first qubit, you have one Pauli operator. Acting on the second qubit, you have another one. It could be any of them. It could be the identity X, Y, or Z. And you do this for all n qubits, I, n, n. So this is what a typical Pauli operator will look like. And so they have also similar properties to the single qubit operators. So maybe I should just this. We have the following. So if I have G, which is a Pauli operator without any phases out front, it's just a multiplication of the Paulis X, Y, or Z. So, or a tensor of them. So something like sigma I1, 1 tensor all the way. Basically the same thing that I had up here, just this part of it. Tensored all the way to sigma IN. And then what we have is that G squared equals to the identity. I should use I. And then also we have that similarly, so if I have any G or H element of this Pauli group, then again, like they did before, they either commute or they anti-commute. And this basically just follows from the fact that, okay, so the way that you have it defined, you have different Paulis that are acting on different tensor factors of the Hilbert space. So when you want to do the commutator, it essentially boils down to the commutation relations on each factor. And so if each factor either commutes or anti-commutes, then the total operators, Pauli operators, will either commute or anti-commute. And so let's use a useful notation instead of writing out this tensor factor every single time. What I'll do is the following. So G written as above, sigma I1, 1, tensored, sigma IN, N. We will write this as omega times sigma I1, sigma I2. And it should be obvious what's what, just from the fact we're going to keep the ordering more or less. Actually, the ordering doesn't matter because they're acting on different tensor factors. The labeling of the operators will help you to know which part of the Hilbert space it's acting on. So I'll give an example. So so for example, if you have something like Z1, Z acting on the first tensor factor times the identity times X3, then we will write this as Z1 X3, and we will just actually forget about the identity. Okay, so let's move on. Okay, so this is one of the first ingredients of the stabilizer formalism. So we say that a operator stabilizes a state. So if we have some state psi, let it be a pure state in our Hilbert space, then if G could be any linear operator on the Hilbert space in this case, but we will later restrict to those coming from the Pauli group. So if we have that G psi equals psi, then G, we have that G stabilize, we say that G stabilizes the state psi. Okay, so we want to define, so one thing that we're going to look to do is sort of one of our ambitions here is we want to actually label quantum states in terms of operators. The reason being is because eventually we'll see that to actually characterize how the Paulis, to actually characterize Pauli operators will not be so hard. And then also how they change under a certain set of unitaries is also pretty easy to track. So if you can actually specify a quantum state just in terms of the operators that stabilize it, then you can keep track of a whole sort of class of quantum states just through their Pauli operators, which hopefully will be easy to track. That's kind of the idea. So we say that n-qubit stabilizer group S is an abelian What do I mean by that? Just means that all elements commute. Subgroup of the Pauli group, such that, and there's a couple of additional criterion. You can't have, although negative identity is inside the Pauli group, it can't be inside the stabilizer group because it only stabilizes the trivial state psi equals 0 minus I psi always has the same eigenvalue -1 times psi. And then if you impose that this is a part of the stabilizer set, then it means that it must equal psi. But if negative psi equals psi, then this is just saying psi equals 0. Another thing that you must have is that all elements inside of the stabilizer equals 0 for every GH. So this seems like a obvious necessary condition, because in quantum mechanics we know that if essentially to stabilize a state is to say that it has eigenvalue 1 on that state, and we know that operators cannot share the same eigenstate unless they commute. So that's the straightforward second one. We also have that for any G inside the stabilizer, since it's a Pauli operator, and if it's not negative I, which we said that it can't be, that also implies something that I didn't say. It implies that the coefficients can't be plus or minus I, so I will not show that, but so I can take any Pauli that satisfies these conditions. The square of it will be equal to, and I keep writing this, will be equal to the identity. That means that G squared acting on some psi, if it stabilizes, if it's to stabilize it, then, okay, say psi is an eigenstate of this, then you have that lambda squared times psi. But if G stabilizes psi, or sorry, since G squared is the identity, we have that this is equal to this. That's what I wanted to say, or that lambda equals plus or minus 1. Okay, so let's actually look at some examples of this. Actually, some very well-known states can be written precisely in this way. So for example, if I have the Bell state, this is, or one of the Bell states rather, this is a maximally entangled state, and it can be stabilized by, so I will just, we have consider x1 tensor x2, which I said I will write as x1, x2. And also, so when I act x on, sorry, how do I want to do this? Yeah, consider this state and another one, z1 tensor z2, which we will write as just z1, z2. So when we have these, you can check first, you can check that xx zz equals 0. The reason that this works out is that even though x and z don't commute, so how would I work out the commutator for this? I would write out xx zz x1, x2, maybe a little bit more clearly, x1, x2, z1, z2, minus, sorry, the other way around, z1, z2, x1, x2. Even though x and z don't individually commute, what I can do is I can, because these operators acting on different tensor factors, they do commute. I will have something like x1, z1 here, and then x2, z2 here, minus something with the roles reversed. So what you will have is you have two factors which anti-commute, and that turns out to mean that the whole thing. So if you have an even number of factors which anti-commute, then the whole thing commutes. So one thing is to show that I'm going to look and show that these actually stabilize the state, but it's also important to see that they do commute as well. So we're satisfying the properties. Also use that if X is acting on some computational basis state, then what it does is it adds 1 to it, and we know that Z acting on a computational basis state is equal to -1 to the y, something like this. So then we can show that this in fact stabilizes. So XX B equals, well, I just will go up here and look to see that when I act it here, XX will map this to 1, 1, and this one to 0, 0, but the coefficient in front of them is the same, so you get back the same thing. And similarly, you have that ZZ on B will be equal to B. In fact, you can go further. And so this one I won't show, but you can actually, because I mean, it's not hard to show. It's just working out a little bit of algebra. In fact, the two conditions XX. Okay, maybe I will just backtrack a little bit. So this is an interesting fact. So if I have some psi, which is a quantum state on 2 qubits, which I can write as something in the computational basis as like xy, alpha xy. So this is the most general way that I could write it, where xy are bits, zeros or ones. So if just the two conditions, XX psi equals to psi and ZZ psi equals to psi, actually what we get is that this suffices to uniquely determine that psi must be equal to the Bell state that I wrote above. Okay, so, and this is kind of what I was hinting at before. I don't want to do the full proof of it, but the basic idea is that I can take these Pauli operators, and so even though in general a quantum state requires these 4 parameters, alpha x, alpha xy, which can be complex, I completely specified a particular quantum state just by the Pauli operators that stabilize it. And what's nice about this is that I only required 2 Pauli operators to do this, XX and ZZ. And in fact, that's sort of a general trend that you'll find, is that to find the stabilizer state for, any n qubits, you only require n independent Pauli operators. So I'll get to what I mean by independent, but more or less the idea is that you can sort of specify just using a linear number. So it scales linearly with the number of qubits. normally you would need 2 to the n parameters, complex numbers. And here now you just need a linear number of bit strings, just telling you which Pauli operators. Okay. Okay, so just roughly, what did we do? Just to give an overview of, I'm trying to spell out what the general ingredients are for sort of finding these stabilizer states. So more generally, what we kind of have is that we can think of the stabilizer group here as being generated by 2 elements, XX and ZZ, in the sense that I can produce all of the elements of the stabilizer group just by multiplications of these. And it turns out that this stabilizer group consists of I, the identity, XX, ZZ, the 2 generators, and then the operator that you get from multiplying all of these together, which is minus YY. This is the full stabilizer group, and it can be generated more or less, it can be generated by any 2 of these 3 in this case, because XX times ZZ gives you this one, or ZZ times minus YY gives you X, etc. And you can show that because XX and ZZ stabilize psi, then also so will the rest of the elements of the group. So the basic idea is the following. So while we typically require 2 to the n complex parameters, to fix a quantum state, instead, for stabilizer states, we only need to keep track of n independent generators. N independent. This is supposed to be an n. Okay, so we have a couple of questions, like, so how do we find these stabilizer groups, and how do we identify these independent generators? So I will skip through some of this. Okay, so to actually sort of resolve this, we're going to look at something called a check matrix. So consider the following thing. We can think of a single Pauli operator in terms of whether there are x's, z's, or nothing on a particular tensor factor. So I will just start with an example. So I can look at the operator x1, x2, z3, I4, which usually I don't write that, but basically all I have to think about is whether on each tensor factor there appears an x or a z, or if it's a y, then both of them appear roughly, right? Because if you have a y, you can write that as x times z or z times x. So I can map this to sort of just a bit string telling me whether an x is present, a z is present, or both are present. So I will write the following like this. X appears on the first factor. It appears on the second factor. It does not appear on the third factor or the fourth factor. And so this part right here is just concerning the bit string telling me whether I have x's. And then I have a second part of this bit string, which tells me whether a z is present or not. So here I have no z's on the first, no z's on the second, one on the third, and nothing on the fourth. So something like this, and this will be for the z side. In general, I will be able to write any G element of the Pauli. Sorry, no, if I want it to be a element of a stabilizer group, then I will be able to write it in the following way. G will be mapped to some bit string on the X part, A, X, and B for Z. And how many bits do I have on each? So here I have n bits. Sorry, I should use the same color. Here I have n bits, and here I also have n bits. And there's one piece that's missing, which I can append here if I want to, which is the overall sign of G. It could be plus or minus. And so I could also just write it something like this, perhaps, maybe an overall sign R. And so there's one additional bit. So now that we've sort of condensed, so also let me give one other example, just because this might not be clear, that you can also do something with, if you have something like the following, say, for example, y1, y2, x3, and I4. Or I'll just make this Z. So this one can be mapped to, and maybe I'll put a minus out front so that we also see how that works. This one can get mapped to the following. If you have a Y, then that means, and I will put the division right here. So if I have a Y, then I have a factor on the X and the Z side. If I have a Y here, so also here and here, I have an factor on the x3 side, but none, so none for Z, and then also 0 here, 1 here, and also something for the bit. So I put a 1 if it's negative, and I put a 0 if it's positive. So that's another example. So now we can construct this check matrix, which is basically, say I take a candidate set of, so in order, what I said before was to specify a stabilizer state, you need n Pauli operators. So let's consider so actually, if you guys sort of can see what's going on here, what I have is that these arrays of ones, these bit strings of ones and zeros, are actually, I will write them as maybe vectors. I will call it R. And they are vectors in a space of bits, Z2, to the 2n plus 1. And so what I'm saying before is that for some G in the stabilizer group, you can map that to some RG element of Z2 2n plus 1. So now this check matrix, how is it constructed? You take a candidate set of, I said you need n independent generators. By that, I mean n independent Pauli operators. So that actually translates to the following statement. Take the corresponding R's. So if I take a set of candidates, S is generated by some G1 all the way to Gn. I only need n of them. Then I can map that to a set of the corresponding vectors in R in Z2, 2 to the n plus 1, which is going to be like R. And instead of writing G1, I will just write it as 1. These are the bit strings to Rn. And to construct this check matrix, I will basically take a matrix where the rows are given by these R's. And so this is a matrix that's, what's the dimensions here? This is going to be, n rows times 2n plus 1 columns. And so we have the following sort of theorem, which sort of helps us out. If we want to find the independent generators, and that's going to help us specify a particular quantum state, a stabilizer state, then we have this theorem, which says that G1 to Gn are independent if and only if the vectors R1 to Rn, the corresponding vectors, are linearly independent. Or just that A has rank n. Okay, so we can do basically a trivial example in a sense. So going back to S, this is for the Bell state. I said that it was completely specified by XX and ZZ. So by the above theorem, it must be that the corresponding vectors are linearly independent. So what does that matrix look like? So I take the rows. So XX is 1, 1. So I have something like this, XX 0, 0, 0. And then I have 0, 0, 1, 1, 0. Okay, this has rank 2. We can see that that's the case because there's no entries that are overlapping. Therefore, they're linearly independent. And XX and ZZ are both independent generators. Actually, it will turn out to be, and I will just do this quickly and then I'll erase it. Say that I had taken XX and minus YY just for the sake of argument. What will that look like? 1, 1, 0, 0, 0. And then if I want to have YY, what does that look like? It's 1, 1, 1, 1, 1. And in this case, just by inspection, you can kind of see that even though I can eliminate this 1, 1 here from here, I can't eliminate this part. So this also has has rank 2. And they're linearly independent. Okay, so far we talked about the states. Now we want to talk about the transformations or the dynamics, if you will. So let's just look at the following observation, that if G stabilizes some psi, that is to say G psi equals psi, and we perform a unitary on our state psi. So if we perform some unitary times psi, then we can say something about also the stabilizers, because just because G stabilizes it, we have U times G times psi. I can always do this. And then using the property of the unitary operators, I can do U times G times U dagger times U times psi like this. So here I have the state that I started with. And here I have some linear operator, in fact, a unitary acting on it. Therefore, U dagger stabilizes U psi. Okay, for those who are wondering, I did just grab that specific part straight from Nielsen and Chuang, so sorry for lacking any creativity. But we want to restrict our attention to certain kinds of unitaries, because in general, if I just act any sort of unitary, it still is going to be very difficult to carry out these calculations classically. But let's consider the following subset of unitaries. And let's see, okay, so such unitaries, what do they do? What is there such that if I have some element of, if I have some element of n, then what does it do? It takes any Pauli operator by conjugation into another Pauli operator, like so. So this is how we're defining it, and this is called these are called Clifford unitaries. And also, I guess, for the interested, it's the normalizer of the Pauli group, which I will just write like this. Okay, so do we know any of the unitaries that come from there? Do we actually we should be quite familiar with them, because these Clifford unitaries are generated by gates that we already kind of know. HI, this is a Hadamard acting on each tensor factor. This is the phase gate acting on each tensor factor. And then this is the controlled NOT gate acting on any two qubits, not the same. So just to recall, H acting on any tensor factor is like this, whereas the phase gate will be like this. And then we know that the controlled NOT gate acts on two qubits, and it's an entangling gate. Sorry, old habits die hard. But I like the CX because it's just a little bit more compact. This one is a 4x4 matrix because it acts on two qubits. So I will write it in a compact form, but each of these symbols inside the matrix are a 2x2 matrix themselves. So this is 0, 0. This is 2x2, 2x2, and then this is an X like this. So this group, this subgroup of the unitary group, the Clifford group, is generated by these elements. And so let's see how much room I have here. Okay, yeah. So let's remind ourselves how these work. The operation. Okay, so this is more just for some cultural enlightenment and to remind you that, in fact, these do exactly what I said that they do, which is to map Paulis into Paulis. So if I take x1, x2, z1, z2, by the way, I don't really have to look at y too hard, right? Because more or less, I can figure out the action on y by the action on x and z. The output of this will be xx, so x1, x2. So if this is, say, or maybe I should be a little bit more precise. So I, J, if this is acting on the, so if this is I, this is J, this is I, this is J, then this is I, J. This one is just X, J. What do I mean by this notation, by the way? I should again clarify that I is the control, J is the target. Z, I, and Z, I, Z, J. And then we can sort of fill out what some of the rest of these. Hadamard maps X to Z and Z to X. Phase maps X to Y and Z to Z, so on and so forth. Okay, yes. So now, so we have this idea that, say I have a check matrix given in this form. Now, if I perform one of these unitaries, how can I sort of update what I know about this thing? And how difficult is it for me to do that? Well, essentially, what you need are these rules right here. These are the update rules. And then what you can do is the following. So let's consider first the elements of this one where it only acts on a single qubit. So let's consider G acting on the kth qubit, which is an element of the Hadamard. The phase acting on that, or it could be any of the Paulis too. We will not discriminate. Any of these acting on a single qubit, then what we have is that to sort of update our check matrix, our set of generators, all we need to do is update the Pauli acting on a particular factor. If this is the kth factor, all I have to do is update. I have to just update that that position for all n generators. So I will just say this, I guess, verbally, to update. Okay, sorry. Let S be a stabilizer. Group. Then what we have is that the action of G, what it does is it maps S to GK S GK dagger. And this induces a map of psi to GK psi. But we're not going to worry about the psi part because the the S completely fixes what psi is anyway. So all we have to worry about is what GK does to S. And to figure out what that is, all we have to do is, like I said before, if I look at this, so if I look at a concrete example, if I have, sorry, up here perhaps, yeah. So if I act some Hadamard on my operators, all I have to, and say it's only acting on the first qubit, then all I have to do is modify the kth position, or in this case, the first position for this, and maybe a sign flip. So I have to only modify, let's see, a linear number of places is, I think. So the basic idea is that there's n possible rows, and I just have to modify the elements in these columns here. And so there's like, let's call it, I'm just trying to find room on the page. Okay, so let's say it like this. So to update S, or equivalently psi, it suffices, we just need to update the kth position of the check matrix. To update the kth position of the check matrix for all n generators, of course. And roughly, this will be sort of in the computer science notation, this is something like a linear factor. Just I believe it's 3n, right? It's 3 columns that I have to modify. And there's n rows, so 3n. So there's 3n steps that need to be taken. If I have an entangling gate, if G is equal to Cxij instead, then I have to update positions K and K. Oh, sorry. Let me write it like this to be consistent. Cx K prime. So I have to update positions K and K prime because the controlled NOT gate by these update rules only changes the control and target qubits. So we just need to update those positions. So we still have something that's like order of n complexity, meaning roughly the number of steps you need to do. Okay, so far everything is quite nice. What we have is a state of affairs where you have a check matrix and you can sort of specify a complete quantum state by how many parameters. So you have here how many bits? You have n times 2n plus 1. So this one is something like, in terms of space complexity, maybe I should, this is like 2n squared plus n. So this is roughly goes like n squared. Here we have that the complexity goes like order of n. So roughly, if we're just looking at a quantum state and updating it with Clifford unitaries, so stabilizer state plus Clifford, this can all be done in order of the number of operations that you're going to do, which, so it's going to be something like, let's see, I have it's going to be something like n times, I think it ends up being n cubed, right? Because you have however many, sorry, 1 second. Now I don't think that that's right. That's why I'm sort of checking real quick. Okay, that's for a single operation, but what if I have more than one? Then maybe if I do maybe m Cliffords, so maybe it's something like m n cubed. Okay, I will actually check this. I'm a little bit suspicious because it doesn't strike me as a familiar sort of complexity. Maybe I'm wrong somewhere with how I did it. Anyway, but so it's something that's polynomial, which is important. Okay, the last element is measurement. So we want to restrict ourselves just like we did before. We restricted the possible observables. We want to restrict to measurements of Pauli observables. So Pauli observables. So we know that they have eigenvalues. So or so the spectrum of some G, where that's a Pauli operator, is an element of plus or minus 1. Probably it's gotta not have phases, so without the phases or something. Okay, so, and to perform such a measurement, we have that the projector corresponding to such an observable, it can be plus or minus 1, and the projector is something like the identity. So this is acting on a particular tensor factor, right? I plus or minus G. So now we have two possible cases for how we want to measure this. Say that we have, let S be a stabilizer group. And we perform a measurement of G, then what will happen? Either there's two options, either G commutes with all elements of S, or G commutes with G commutes with one or more anti-commutes, sorry. Anti-commutes with one or more generator of S. Okay, so we take the second condition first. It's a little bit easier to analyze. So if you have more than one generator, so we have that S is generated by G1 all the way to Gn, right? This specifies a quantum state. By the way, so as a side remark, I've been considering stabilizer states specifically, but you can consider if you have an n-qubit Hilbert space and you only specify less than n independent generators, you specify a subspace of the Hilbert space that's stabilized by those generators. And in general, it won't be a unique quantum state, but it'll be a space, sublinear space that's stabilized by those generators. So that's important for quantum error correction. I haven't really focused on it because it's not entirely going to be important for some of the stuff that we're looking at with classical simulation. Yeah, so it is worth mentioning that there's more to this. And there's a greater variety of sort of like stabilizer operations in a sense. Okay, so let's take the second one first. If S is has these generators, and we know that we have some G which anti-commutes with at least with perhaps more than one. G comma GI equals 0 for I something like this. There's the following argument, which is easier to explain with an example, which is that we can always restrict without loss of generality. Without loss of generality, we can consider the case where G anti-commutes with just one generator. Okay, that seems kind of hard to believe, but so if we just sort of look at an example, the idea is the following. Say we again look at the state. Say we take G equal to Z1. Yes. So this is, we want the observable Z1 to be measured, and we have a stabilizer group which is generated by XX and minus YY. So I could have done this slightly differently. So you see clearly that you will have that actually Z1 anti-commutes with XX, X1, X2. Sorry, that's the wrong symbol. And it also anti-commutes with the other one. Why? Because on each of the tensor factors, there's only an odd number, more precisely, just one of the tensor factors anti-commute. Z1 is the same thing as Z1 tensor identity. So on the second tensor factor, everything commutes. On the first tensor factor, Z anti-commutes with X or Y. So this whole thing anti-commutes. Z1 minus YY. Okay, so that seems like we can't just restrict to, but what we can do is the following. The full stabilizer group looks like what? It's I, XX, YY, sorry, minus YY, minus YY, ZZ. And so what it turns out you can always do is that if you have more than one generator that anti-commutes with G, the observable that we want to measure, then we can always rearrange the generators such that the only one generator is anti-commutes. So in this case, you could rewrite the generators as instead being XX, ZZ, and clearly ZZ will commute with Z1. And so this is a more general pattern, and you can always do this. So without loss of generality, you can just consider the case where G anti-commutes with just one generator. So then you can essentially do the following trick. So if you measure it, you get some answer plus or minus 1. When it anti-commutes, okay, so this is something to also remember, that if it anti-commutes, then it doesn't stabilize that state. So psi, the state that's stabilized by S, is not an eigenstate of G. So therefore, a measurement of G will actually perturb the system. And so you will, in general, get a new stabilizer state. What is the new stabilizer state? The way that you actually update it is the following. So first thing is you have S in terms of the generators, G1 to Gn. And in the second step, you rearrange S, you rearrange the generators G1 to Gn so that you have at most one that anti-commutes, call it G1, and then the rest G2 prime, Gn prime. These all commute with G. You can do this. And then 3, you replace G1 with plus or minus G, depending on the outcome of the measurement. Right, because once I measure G, what am I doing? I'm projecting it. I'm projecting it, that particular tensor factor onto an I'm projecting it onto the plus or minus 1 eigenstate on that tensor factor, or rather, tensor factor is not the right word in this case. But I'm projecting it onto the plus or minus eigenspace for this operator. So yes, so then we can just replace the operator that it anti-commutes with the one, and now it commutes with everything else, and plus or minus g tells you specifically which part of the eigenspace that the new state psi will reside in. In general, this also, the part of this that's computationally expensive classically is the following, which is that if I have more than one that anti-commute, to actually rearrange things to find this, to find the new set of generators where at most one anti-commutes, this requires roughly n squared steps. So this is a one computationally expensive part. And then two, if we go to the part where things commute, then if everything commutes, then the only thing you need to really care about is whether the outcome of the measurement is plus or minus g. So we just need to figure out, we can keep, so if they commute, then actually S stays the same. And now we just need to figure out whether psi gets mapped to plus or minus psi. And this you can show actually, this procedure is actually turns out to be quite costly. And so what we're going to talk about in the next, by the way, there's no talk next week because it's spring break, but in the week after, we will discuss this paper by Aronson and Gottesman, called Improved Simulation of Stabilizer Circuits. I might have butchered the name just a little bit, but it's something along these lines from 2004, I believe. And so one of the major sort of results of this paper is that you can, so in the standard way, this requires the complexity of updating this is n cubed. And I believe that the result of this paper is that they can make this go to n gamma's less than 3, but I don't remember if it was 2 or something between that, something like this. So that's what we'll talk about next time, and but still, even with all of this, you still have that the updates of the measurements are polynomial in the number of qubits, n cubed or n squared. So the whole thing is still requires just polynomial steps or updates. So then we have this theorem. Which basically says the following. Any quantum circuit consisting of stabilizer states, Clifford unitaries, and Pauli measurements. So any measurement, quantum circuit consisting of these elements can be efficiently in Pauli space / time simulated in a classical computer. And more or less, we kind of, in the standard way, we kind of proved it as we went by looking at each of the constituents. We looked at the fact that you only need roughly n squared bits to store a quantum state through this check matrix. Then you need only linear number of steps, sort of operations to update under Clifford unitaries, and then sort of n squared or n cubed when you perform measurements. But the whole thing put together is you're still being able to actually simulate these circuits in polynomial sort of resources, for lack of a better term. So that's the Gottesman-Knill theorem. And so a lot of subsequent work has been done to go in a couple of directions. The one thing that we'll talk about next time is using less resources for these updates. That's one way that you can go. The other thing that you can do is to say, okay, well, what if we go outside of this set of constituent parts? Maybe we go for different unitaries or something. We know, for example, that the addition of a T-gate promotes you to universal quantum computation. So if you include some non-Clifford gates, how well can you simulate things then? What is the resource cost of trying to simulate depending on the number of T-gates in your circuit? That's the sort of questions that people are asking. And so that's one of the things that we'll talk about when we return, when we return in 2 weeks. Okay, any questions? Miss? Okay, seems that everybody is quite satisfied with the state of affairs. Okay, if there's no questions, it's Friday, so we will not take up any more time. Okay, have a nice weekend.